In earlier lectures, we discussed at length some ways in which charges are sources of electric fields. Today we'll begin to discuss how charges can also act as sources for a second field, the magnetic field. Here's a key point. Charges must be in motion in order to be sources of magnetic fields. We'll start today with the case of a single moving point charge as the source. Let's first look at some computer visualizations. Here we see a positive charge moving roughly from left to right, and at various points in space, we show arrows representing the vector magnetic field generated by this moving charge. Let's notice here that the field is pointing in directions that are quite different from the direction the charge is moving. In particular, notice how the magnetic field is curling around the moving charge's path. From our point of view, the magnetic field is curling around the path in a counterclockwise direction. Look now what happens for a negative charge of the same magnitude with the same velocity. The magnetic field is again curling around the negative charge's path, but in a clockwise fashion. We'll be able to handle these differences, but for now, let's note the curliness of the magnetic field is a very general property that we'll see repeatedly in the future. Let's now focus on a single charge Q that is moving with a velocity of vector v, and for some observation location located by position vector r relative to the charge, let's start to figure out how to compute the vector magnetic field, vector B, at that point. We're going to first discuss computing the magnitude of vector B. The magnitude is proportional to the magnitude of Q and the magnitude of the velocity, that is the speed, and inversely proportional to the square of the distance from the charge to the observation location. The constant of proportionality can be written as mu over 4 pi. The SI unit for the B field is the Tesla, which is a Newton second per Coulomb meter. In the SI system, mu naught over 4 pi is equal to 1 times 10 to the minus 7 Tesla meter second per Coulomb. Let's now discuss how to figure out B hat, the unit vector that describes the direction of the magnetic field. The direction of vector B depends on both the directions of the position vector r and velocity v, which we can describe by r hat and v hat respectively. B hat is equal to the cross product of v hat with r hat times the sign of the charge q. Now, it would be a good time to review how to do cross products, which we learned earlier how to do in our study of mechanics. Let's recall that we can use the right-hand rule to determine the direction of a cross product, and let's use v hat cross r hat as our example. Notice the two vectors v hat and r hat lie in a plane. The cross product of v hat with r hat will be perpendicular to that plane. To find that perpendicular direction, follow these steps listed here. You may wish to pause the video here to give it a try. Here's a second thing to try for reviewing cross products. This URL leads to a program that shows arrows representing vectors involved with a cross product. Here, red is the cross product of green with blue. We can change the vector represented by the blue arrow and see how the cross product changes. Feel free to access this program using the URL shown here. We also have 2 mechanics lectures showing how to compute cross products for the physical quantity of torque, which is the cross product of a position vector, r, with a force vector, F. Now, this is a completely different physical quantity from the cross products like v hat cross r hat that we'll do in this course. However, the procedures for computing cross products are the same, so you might like to review those mechanics lectures as a refresher. By applying the right-hand rule to this example, we find that B hat is out of the page, that is, in the same direction as V hat cross R hat, if the charge is positive. If Q is negative, then B hat points oppositely to V hat cross R hat. That is, for Q negative in this example, the direction of the magnetic field is into the page. The description for vector B can now be pulled together into a single expression called the Biot-Savart law. Let's work that out. Vector B is the product of the magnitude of B times B hat, the unit vector. And here is that product, just collecting our results from earlier in this lecture. We can simplify this a bit and end up with this statement of the Biot-Savart law for a single moving charge. Let's try to use this result to answer this question. We have a negative charge moving as shown in the plus x direction. What's the direction of the magnetic field at the observation location marked with an X? Stop the video and try to answer this before continuing. We know the direction of the magnetic field is given by V hat cross R hat times the sign of the charge. Here's an arrow that represents R hat. V hat points in the same direction as vector V. So, using the right-hand rule, we find V hat cross R hat is into the page. The charge is negative, so we need to multiply V hat cross R hat by -1, which flips the direction. So B hat is out of the page. Thus the answer is this. B hat points in the plus Z direction. That's it for now. In our next lecture, we will discuss how to describe the magnetic field due to a collection of moving charges known as a current.